Okay, hey guys, so hopefully this whole thing works this time. I think that I've recorded myself saying this lesson 3 times now, and hopefully this one actually works. Okay, so I'm looking at book 7 here, lesson 7, and there's something I just want to introduce to you. So whether you write this on the back of the booklet or on a piece of paper and staple it to it, just for your extra understanding. So basically it's looking at how we can write notation out. So if I have, let's look at the function y equals 1 on x. And if we express what we want to look at, how it approaches towards 0 and towards infinity, this is how I want it written, and this is how it's typically seen to be written in HSCs. So we know that if we look at as x tends towards infinity, that's looking along here as x is getting towards infinity. Now, if you want to look at x going the other way, we know that that would be just x tending towards negative infinity. If we want to look at what's happening as we approach the inwards, we are approaching 0, but we distinguish between approaching 0 from the positive side and the negative side, and that's written as x approaching 0 from the positive side, which would be here, and then x approaching 0 from the negative side, which would obviously be over here. So that's what that means, coming in from either side of the axes and what's happening to the function. Alright, so now in saying that, let's look at it in terms of this. So let's say we could write in an exam what's happening as x approaches 0 from the positive direction. Well, we know that our function y, as x approaches 0 in the positive direction coming in here, our function is increasing infinitely towards infinity. We know that as x is approaching 0 from the negative side, we can see that the function is decreasing infinitely. If we were looking at what's happening as x approaches infinity, now technically x approaching infinity could be all the way over here, and I'm looking at values of x going this way, but typically if we were to do that, we'd be talking about as x, that's similar to x approaching 0 from the negative side. Another way some people write it is x approaching infinity from the positive direction. Generally I just stick to, are we talking about approaching 0 or are we talking about approaching infinity? So you won't see me use that notation a lot, but just in case it does come up, that's what it means. X approaching infinity, looking at the positive x values. And we can see that if we are looking at what happens as x approaches infinity, x is getting bigger and bigger, our function is approaching 0. And then same idea, as x tends towards negative infinity, our function tends once again towards 0. So that there is the terminology that I just wanted to recap with you and show you if you weren't sure about it already. Okay, now in saying that, let's have a look at the booklet. So to start with, we're looking at drawing y equals e to the power of a function when you're given that function. So let's think about our exponential graph to start with. Okay, good, I'm still recording. We know that our exponential graph crosses at 0. We know that, I think I just said crosses at 0. We know that it crosses at 1 when x equals 0, which is what this function notation here means. We can see, and we already know, that as x is getting big, we can see that the graph is getting very big. And as x gets very small, as x heads towards negative infinity, we can see that the graph approaches 0. One key thing that's standing out here is we know that there is an asymptote at y equals 0. So y cannot equal 0. That gives us our asymptote. And we can see that there are no values for negative y values here. So no x value, no matter what we put in, whether it's positive or negative, will give us a negative y value. Okay. First example, keeping all of that in your mind. We've got x minus x squared and e to the power of f of x. So what I'm going to start by doing is showing you a quick, simple way to do it on quite easier ones, and then a way that might have more work. Now, our x-intercept here at a half is going to give us the same x-intercept here at a half. And if the y-intercept is a quarter, when we put e to the power of a quarter, it's just going to change it, the y value. E to the power of a quarter is a bigger number. Let's see what it is approximately. .28. There we go. So we can see that that's why it is sitting above. Now, we know that the exponential curve has to cross through 1. The only time, we learn in advance, the only time the exponential curve will not cross through 1 is if it is in the form ae to the x, where a is a number other than 1, or plusing with c, where c is a number other than 0. That's when we know that we don't have an intercept on our exponential at 1. However, you will find in this entire 4-unit course, we are looking at most of the time just e to the f of x, which means that our intercept is at 1. The only time it won't be at 1 is if there is an asymptote there. However, 99% of the time it means it'll cross through at 1. Okay, now we can see that we have our new stationary point, we have this intercept. Our stationary point was a maximum, it remains a maximum. Now, what happens as x approaches infinity? Then we can see that our function, if we subbed it into our function, then f of x is going to approach negative infinity, which means that if we sub that in to e to the f of x, that's going to just give me values. Now the negative makes them fractions, so the bigger the value of f of x, the smaller the fraction is going to be, which means that I'm going to get closer and closer to 0. And again, if we sub in, if we look at x approaching negative infinity, same idea, we will get f of x approaches negative infinity. So therefore e to the f of x approaches 0. So that's how you know it comes down to your asymptote, approaching your asymptote at y equals 0. Alright, next one. Okay, so here we go. We've got an x value at 1. So we know that our stationary point is along that line somewhere. Now, if we're looking at subbing in 1, we know we get negative 1 in our function. So we're going to get y is equal to e to the power of negative 1, which is equal to 1 on e, which is approximately 1.5, which tells me that if 1 is here, half is here, here we have my minimum. Y equals e to the x means it crosses through at 1, so it crosses through here at 1, it has a minimum here. Now, there's no other information to tell me it does anything otherwise than that. However, it won't hurt to just sub in, whether you're subbing in a value here, or let's look at as x approaches infinity. As we sub in infinity positive numbers, f of x will also approach infinity, which means that e to the f of x will approach infinity. And because it's squared, when we sub in negative infinity, f of x will come out as positive. So e to the f of x come out as positive. Oops. Sorry about my messy handwriting. I can definitely say I'm neater on a whiteboard than on this, but I guess it'll just take some getting used to. Okay, so we know that it just will come up and continue to proceed infinitely. Okay, moving on. Now it's getting harder. It's really testing our deep understanding by not giving us the equation of the graph and instead just giving us the image. Okay, so thinking about what we know so far. Let's look at as x approaches as x approaches 0. From the positive side, we can see that as we are getting closer to 0 from the positive side, that our function approaches 0. Okay, so then let's look at x approaching 0 from the negative side. We can see that x approaching 0 from this side also approaches 0 for our function. Now, in my HSC, I haven't been mentioning your layout of your working, but I would be showing all of this to the marker. Shows that you really know what you're talking about, and it sets it out quite nicely. Alright, so now let's look at as x approaches infinity, positive infinity. As x is going out this way, my function f of x seems to be tending towards 1. And then as x approaches negative infinity, we can see that my function f of x is not restricted by that asymptote. It is continuing up to positive infinity. Okay, now let's look at how that changes on our e to the power of f of x. So e to the power of f of x. Well, if f of x is approaching 0, e to the power of 0 is 1, so that means e to the power of f of x approaches 1. If, same idea here, e to the power of f of x will just approach 1. Then we have f of x approaching 1. Okay, so e to the power of f of x. Well, if f of x approaches 1, e to the power of 1 is e, so e to the f of x must approach e. And if f of x is approaching infinity, e to the power of f of x will just approach infinity also. So now let's put all of that onto this graph. Okay, so we know that as we are approaching negative infinity, I'm heading up. Now I'm going to put it in, my working out I'm going to put in orange. And I'm going to erase that. So I know I'm heading up somehow as I'm going further into the negatives. So I go, okay, that's that part done. I know that when I'm heading into the positives, I'm approaching E. Okay, so where's my line E? It's about approximately 2. So I know that I am needing to approach this as I'm heading into positive infinity. Alright, now let's look at our zeros. As we're heading from the positive region towards 0, we need to head towards 1. So we need to head towards 1. Now if we're coming up here, it's going to be heading down in this direction. Okay, and then if we're heading in from our negative region towards 0, we're going to be also heading towards 1, so it's going to be coming down like that. Alright, so now I'm going to grab my pen and go, okay, that tells me that it's going to look somewhat like that. There's my graph. Now, I can, if I was given the equation, I could find my point of inflection here by doing my second derivative. Otherwise, that's the only really other piece of information that's necessary for that graph if you were given the actual equation. There's no other intercepts, there's no other piece of information that are necessary to put on it. Okay, so I want you to draw 1 on X. You should know what that looks like. Okay, now I want you to pause the video and do for yourself what is happening to X, what is happening to 1 on X as we are coming in from the positive side towards 0. Then what happens to e to the power of 1 on X. Then do the same thing as we approach it from the negative side. And so on. From X approaching infinity, what happens to 1 on X? E to the power of 1 on X. So pause the video right now and have a go at those. Okay, so assuming you have just completed these yourself, checking them with mine, and I'll explain mine as I go just in case you did get any wrong or you aren't sure on any. Okay. Whew. The first row is easy. You're just looking at this picture here. What's happening as we approach 0 from the positive side? Our function is going up to infinity. What's happening as we approach it from the negative side? It's going down to negative infinity. What's happening as we get towards infinity? Our function's approaching 0. And the same this way, if we go to negative infinity, our function approaches 0. So that first line is very straightforward reading off the graph. Okay. Let's look at now what happens if we raise that to the exponential. If we have e to the power of an infinite number, we're still going to get infinity. This one's interesting. If you have e to the power of negative infinity, you need to be thinking about, well, what's going to happen to that value? Because we know that there are no negative y values when we plug that in. If you're plugging in smaller and smaller and smaller numbers, think about this as a side note. If I plug in e to the power of 1 on negative 2, that's e to the power of negative a half. Okay, if I plug in, let's think about just the power. If I plug in negative 5, that's negative a fifth. Negative 10, that's negative a tenth. Plug in negative 100, negative a hundredth. Notice how all of my fractions, the more I'm heading towards negative infinity, they're getting smaller. So what's happening is e to the power of that is just going to mean that e is getting a closer and closer, its power is approaching 0, because all my fractions are just getting smaller to smaller to smaller, all the way down to 0. So it approaches 0. Okay, if we're approaching 0, anything to the power of 0 is 1, so it means my function is approaching 1, and the same here. let's put all of that onto our graph now. The easiest way I have found by just experience is looking at your infinity first. So I'll grab my working out colour. So okay, I know that as I'm going towards positive infinity, I'm approaching 1. Whether that's the point 1 or the line 1, I'll put it in. So I know that as we are coming, I'm approaching 1 somehow, whether it's going to be like this, or like this, like this, or like this. I have to approach 1 as I'm going out of my graph. Okay, so that's that and that looked at. Now I look at, okay, what's happening as I approach 0, as I approach 0 from the negative side. So it's coming in this way, I'm approaching 0. Okay, so I have to come down and approach 0. If I am coming in from my positive side, I'm approaching infinity. So the only way I can approach infinity is if I'm up here approaching infinity. Put that all together on my graph means I'm going to have, put this one on, approaching infinity up here, approaching 1 this way, then approaching 1 up here, then coming down and approaching 0. What do you find here? Now that's not a great picture. Ooh. Oh my goodness, what have I done? Control Z. Nope. Let me do that part again. So my graph is looking like this on this side. Okay, now it's got to approach 0 and then come up and approach 1. Now it can't ever equal 0, so that there is just a bad spot in our horizontal asymptote. Okay, and that is fine. It's just part of the graph. It's annoying, it's complex, but it's just part of the graph. And if you put that into Desmos, it'll do the exact same thing. Okay, let's moving forward. Now we're looking at graphing the log of x. So let's think about our characteristics of our log graph. We know that our log graph crosses here at 1. So our x-intercept is 1, so log of 1 is 0 is what that's saying. There are no values in the negative x, which means that x must be always positive. And there is an asymptote at x equals 0, so x can never equal 0 is something that's missing. You cannot take the log of 0. That is the same idea as dividing by 0. You just cannot do it in maths, okay? So never take the log of 0, it's an asymptote. And you can see here that as x goes to infinity, our log is going to go to infinity. It doesn't approach anything. I think that's something that came up in class the other day. You won't ever approach anything. You will increase infinitely. And as x tends towards 0, our function heads towards negative infinity. So now let's think about this idea of what's happening now if we're given x minus x squared and we're graphing the log of that. Our x value for our stationary point remains the same, but as you can imagine, the log of a half is going to give us a different number. In fact, it does give us a different number, not just a different number, but different sign. If I take the log of 0.5, I'm going to get approximately negative 0.7, which tells me that it's around here somewhere. Then, oh, hang on, I'm a bit off there. Around here. Now, nothing is affecting my log graph, which means I know for a fact that nothing in this region exists, and I know that it cannot hit my asymptote. So I have a maximum here. We have the same concavity, and it approaches this asymptote. The only thing that we can see coming through here is that it will continue down this way. It does not hurt to plug in a value on either side, maybe plug in a quarter and 1, and see what's happening on either side. Something else a lot of people might do, which I think you'll find takes a bit more work, is just take the derivative of your function. So we have the log of x minus x squared. Remember, the derivative is just put the derivative on top. 1 minus 2x on x minus x squared. If you sub in the x value of 1 and a quarter, you'll find that you'll have a negative gradient and a positive gradient for those values. But I do find that it's less work to just sub in an x value. Okay, I want to go into a bit more depth with this next one, okay, just because it is a bit trickier. So, a few things. I'm just finished rubbing out from my previous attempts that my recorder didn't record for. Okay, so the first thing I want to look at, think about on this value, we know that we can't take the log of 0. So if we have to find what are we, x squared minus 2x. We know that x squared minus 2x cannot equal 0, which means that if you solve that x cannot equal 0 or 2. Okay, what does that tell me? It tells me that they are asymptotes, but I will get to that. We know that it cannot not only equal 0, it has to be greater than 0. We know that when we take the log of x, that x must be not just not equal to, but greater than. So, let's solve this. If we solve this, we're going to get x is 0 and 2. A quadratic and an inequality, we spoke about this a couple of lessons ago in extension 2. We need to test. If I test the point 1, 0, that's right here. I plug that into my inequality. I get 1 squared minus 2 lots of 1, and that needs to be greater than 0. And minus 1 is not greater than 0, therefore it is all this region this way and all of this region this way. So therefore, this graph exists where x is less than 0 and where x is greater than 2. Okay, so we know that basically, if I was to put this on my graph so far, we know that we have asymptotes at 0 and 2. And we know that in between there, nothing is happening. So I'm putting those lines in. You don't have to have those lines on your graph. I'm just putting them there to show you. Okay, now, the next thing. We know that there is... Oops. What is going on? Just bear with me. Okay, so don't exit or stop listening. Maybe just fast forward to when you hear my voice again. I think Word has decided to stop responding because my questions are missing now. Just bear with me.